So is my screen visible?
Yes, sir, perfect.
Yeah, okay. Thank you. So just let me give you the content. Just we will see the background and motivation and various examples of biomedical signals, and more importantly, the objective of biomedical signal analysis is very important. And using this, we will see some case studies via coding itself. So as we know, biomedical signal processing is an application of digital signal processing. So why we need to study about this means the demands of healthcare and health systems are increasing worldwide and are undergoing intensive reforms. But however, the health system success is depending on the proper medical diagnostic techniques. So lot of medical diagnostic techniques are evolved. So absolutely, the success of all these healthcare systems are depending on this. So for example, the clinical electrocardiogram developed by William Einthoven is a new milestone of this medical diagnostic technique. So you can see he is Mr. Einthoven. So that time, this is the ECG device. You can see in the solutions, he has placed his legs and legs as well as hands to manifest how the electrocardiogram can be collected from the device. So this is how he has showed that was that time. But nowadays the technology was evolved. We should thank to VLSI technology. So now easily with just a handheld device, nowadays we can get our ECG signals easily. So the nature of biomedical signals, if you consider, each system in our body is made up of several subsystems, and each of these subsystems carry different kinds of physiological processes. For example, if you consider a cardiac system, a rhythmic pumping of blood throughout the body of this cardiac system facilitates the delivery of nutrients and pumping blood through the pulmonary system. Or, for example, if you consider any physiological system inside us, that the nature of that can be understood by the signals which they delivers. Might be the physiological process are biochemical, electrical, or physical. So mostly we are here intended to understand the electrical manifestation of different organs. That is what actually the biomedical signal analysis. Various organs are there inside our body, so we have to understand how they are working, whether they are working in a correct situation or any pathology was occurred. That can be understood by the electrical manifestation of that organ. So we need to analyze the extracted signals. So various different examples of biomedical signals you consider. The basic component of all biomedical signals is action potential, and derived from this action potential, we can find various other signals like ECG, electrocardiogram, electroencephalogram, which is used to find the electrical activity of the brain, electromyogram, which is used to understand the activity of muscles and nerves of a site, electrogastrogram for understanding the abdominal region, phonocardiogram to, to understand the heart sounds, whether any murmurs are present or not, and carotid pulse, which is actually a pressure signal. You can find it a nerve which was placed here at the position at the neck. Okay, so which will give us some information regarding how your heart is working properly or not. That can be understood using this carotid pulse itself. So you can see the relation between PCG, heart sound, ECG, that is electrocardiogram. It refers you one cardiac cycle, that ECG, as well as the carotid pulse. So all are having some synchronous thing. So S1 and S2, your lub and dub, those sounds, that lub dub sound, one lub dub sound creates one cardiac cycle, and where you have the most contraction, where whenever you are getting uh, pressure via blood pumping, there you will get a peak at your carotid pulse. That is maybe after your lub sound. So this ECG, maybe for some time it is our of interest. We will understand uh, most of our experiments via this ECG analysis. So I think most of you have known about this ECG. Those who have not understood this ECG, I'll let you know how we got these important epochs like P, Q, R, S, and T. Later I will explain you. And this is about EEG signals collected from various channels on the scalp. On scalp, various electrodes will be placed, and they will collect our our electrical activity of the brain via EEG. So, for example, F signals represents your frontal lobe, central lobe. C represents parietal lobe and occipital lobe. From various lobes, clinician will collect different kinds of signals, which will reveal the nature how our brain is working. And because each of these lobes are responsible for various given tasks. For example, if you consider the occipital lobe, they are responsible for our visualization purpose. If there is any abnormality in your O1 and O2 signals, you may say that there is a problem with your vision. Likewise, each of these lobes are responsible for various activities of the brain. So this is very important. What is the objective of overall biomedical signal analysis? That you can understand via this block diagram. Maybe the above portion is responsible, like this is for signal acquisition. So any patient is there, by placing some electrodes on the patient in an environment, a clinical environment, they will collect the signals and they will do some pre-processing tasks to give us the data. So this is what we are interested before processing. So what we are going to do is, if I got some signal here, to find whether the signal is normal signal or abnormal signal is, for example, your objective. That is what a computer aided diagnosis. I have given a signal, I have to process this signal to say whether the signal is a normal signal or any kind of abnormality is presented. So to achieve this, I need to follow some steps. So those steps are given here. What are those? First, you need to filter to remove some artifacts. Maybe whatever the signal you have received, that signal might be added with some noise or some unwanted kind of signals. We need to remove them. Later, we have to find some important events or components of a signal. Say, for example, I have shown you this ECG signal. I said this one signal represents one cardiac cycle, that is one lub and dub, the complete pumping mechanism for some time. For example, to understand, so if you see any abnormal signal, there would be some changes in this particular signal. So how can you find those changes? So first you should know what is the normal situation. So that can be understood via the important events like P, Q, or S and T. If there are any changes with this particular PQ or ST, you can say that there is an abnormality in the given signal. So detection of events is important. Later, to do the pattern analysis, pattern classification, we have to extract some useful information from the given signal. Of course, that is a raw signal, ECG signal. If I just want to process the ECG signal of 10 minutes, say for example, for 1 minute or one mm, segment of that cardiac cycle represents, say for example, 300 samples. Maybe that is less than a minute. If I want to process 1 hour of such kind of ECG signal, I'll be end up with, maybe if it is 1 minute for 300 samples, I have to approximately 60 into 300 samples I have to process, which is a huge amount, because I just don't want to carry only one signal. Maybe a lot of signals I have to process. So instead of doing that, what we used to do is, first we have to extract some useful information, which is actually an important step lies in the machine learning process. That is called feature extraction. We will find the events and we will collect some important features and we'll do the pattern classification. So now what I am going to do is, I will do all these steps here in our particular this session. So we will collect some signals, and then we will do some filtering operations. Later we will try to identify some events, and later we will find some features and do the pattern classification. All these things I'm going to do. So which is why we need to go for this computer aided diagnosis, because it is easy. You have to use just computers, so this will reduce the burden on the clinicians because they have to inspect manually all the signals, which is fatigue, and which actually gives you some quantitative analysis rather than some qualitative analysis. It also helps a clinician as a second opinion. So for example, if you see, these are some ECG signals of various types. If you want to process them, if you want to see just looking into these signals, and if you want to classify them, it is very difficult. Say for example, this is one class of ECG signals called non-ectopic. All these beats are non-ectopic, but morphologically they are different. You see, one ECG segment follows one pattern, another ECG signal follows another pattern. So just by seeing this, you cannot give any response. So to come to one conclusion, we need to identify or reveal the inherent patterns of those signals. So that is what biomedical signal analysis or pattern classification we use here. So as I told you, this is a low frequency signal. In a low frequency, if a low frequency noise adds into your ECG signal, what will happen? This kind of wandering you will observe. Basically, your ECG signal must be like this, but here you are getting some wandering. This is might be whenever we are collecting data from patient, maybe due to some motion of the patient, that data gets added. Some muscle signals get added. We have to remove it. Okay. Or maybe here in this signal, just by looking, you don't know. If you observe its power spectrum, where you can find some peaks at 60 Hz. So that 60 Hz noise is gets added. Basically, the majority of the signal power of ECG lies in between 0.5 to 45 or 50 Hz, the bandwidth. Above that, we will say it is some high frequency noise, and below anything, we say it's a low frequency noise that gets added to the signal. Our interest is we have to confine our signal into this bandwidth. We just want to remove the other artifacts. So maybe let us do such operations via MATLAB. So actually, most of this content I have collected from the textbook called Biomedical Signal Analysis, which was authored by Dr. Rangaraj Rangayan. And the biomedical signals, what I have considered for our experimentation, are also from his repository. What just we have taken the signals from the repository. And just before going into this hands-on, just may I know whether you people are able to follow what I am saying? Just with your response, say yes or no, at least. So far, what we have discussed is the objective of biomedical signal analysis, and we are now going to do each of these objectives. Participants, I hope you're following. Thank you very much.
Yes, sir.
Okay, thank you very much. Okay, let's do the thing. So the first thing is how we are going to proceed the hands-on session, which contains this content. First, we will plot some signals. So just how to plot a given signals, and finally later we will do some operations like ECG peak detection, and we'll do some frequency domain analysis to understand the frequencies which lies on ECG, and later we will do this filtering, detection of events, and pattern classification. All these components we will do. So as I told you, these are the references I have collected. From here, I have taken the signals. Okay. So to plot signals, the commands what we use in MATLAB are, first to extract the load signal, we have to use the command called load. And for plotting, we use commands called plot and subplot of MATLAB. And what for file formats would be supported by MATLAB for one-dimensional any kind of signals, or maybe you can give a CSV file or .text file, XLS or XLSX, or MAT or DAT files. These are the supported file formats for extracting the signals. So now, so this is something to plot your signal. So the commands like clear and close are helpful. So for example, if anyone who is new to MATLAB can use MATLAB for assigning any value here. A is equal to 1. So the one value got assigned to A, and that value was stored in a workspace. This is just a command window, which is just to do some operations we use. If I write something called CLC, whatever there in the command window will go. However, the variables still save in our workspace. I can easily retrieve back my variable value a is equal to 1. However, if I clear the value of a, clear a, what will happen? The variable got removed from my workspace. So likewise, if I have numerous variables, I just want to remove all my numerous variables workspace, because those are for this previous problem. I don't want to get any ambiguity between the current problem and the previous problem. Hence, I just go with this clear all, which will remove all the variables which were executed previously in the from the workspace. And close all is to remove some any windows other than your kind of, say for example, this is another window of MATLAB. If I just open another window of figure windows, I can close. Now load is a command to extract my data. Maybe I can extract the .dat or mat files using the load command. So let me do till this point. I'm sorry, maybe see, for example, here the problem is there is no file called ECG in the directory. So the current directory where I am working, I can fix using this program. So here I just go and I fix, for example, here I want to perform or here I want to perform, I can fix. Now let me see which signals are available. These signals are available. So let me take some signals. ECG 6 is the data is available. Now that ECG signal is came into your workspace as in the form of array. So if I double click on it, the size of ECG is 4000 by 1, which implies there are 4000 rows and 1 column. Maybe the signal is collected from 1 electron. So these are the magnitude values of my signals, 4000. The sampling rate for this signal is basically 200 H. Okay. So now I sampled this signal. Now, if I plot the signal, the current signal, I can plot using the command called plot of ECG. The signal got. So here in figure window, you can see my ECG signal, which contains around 4000 samples and with various magnitude levels. You can here find the important epochs of ECG, P, Q, R, S, T. They are very important to understand the ECG signal. So which is not one cardiac cycle, but many cardiac cycles of this. But it represents how much time, in what amount of time I am getting all these cycles. If I want to know, I have to change my variable x-axis. So that for that I have to use this my sampling rate. So what I am doing is my sampling rate is 200, which implies 200 samples per second. Each second I have 200 samples. So for 4000, how much I have? So I have to divide it with fs of total length. Total length is 4000. Yes, length is 4000. So this will give me an array of 4000. Now I am simply plotting my signal. You can see I got a signal with time in seconds. It is about 20 seconds. I got these many number of cardiac cycles, and this represents is amplitude. Basically, I should write here amplitude. So if I write command called closer, a figure window will go. There is no figure window. So that is how it helps me. Likewise, you can plot all the given ECG signals. So if you want to see the variations between signals, so let me show you another signal. Even I can run the whole program using this command called run. See, you can see a drastic change in the signal, which clearly shows you that it is an abnormal signal. So let me run another signal. Oh, maybe I got an error because there is no ECG 7. And so let me stick with another ECG signal. Run. So you will get, you see, another kind of ECG signals. Likewise, you can plot the signal. For plotting, you can have a lot of flexibilities. So you can give function name, even input option. So for example, if I run this program, it will ask me in the command window, give the name of the ECG file, which file you want to execute. So I will write here ECG6.dat. Now that file will be executed later, and I got that signal. So this is about the simplest one, how to take the signal and how to plot it. So our first objective is over. So the next one, so these are some of the sample signals you can see. So the next one is we have to find the peaks. What is the importance of peaks? You can see here. The ECG signal, as I told you, which actually tells you, which has a relation between your pumping action inside your heart. That is the simple electrical manifestation of your propagation of excitation pulse through heart. If you see this figure, this is your heart. Heart contains 4 chambers. Above you have 2 atrias and below 2 ventricles. And at this corner, you have something called SA node, sinoatrius node, which is also known as a natural pacemaker of the heart, which actually triggers your heart pumping. When it gets excited, maybe that excitation is controlled by your autonomous nervous system. However, when it gets triggered, what will happen? One electrical pulse will be propagated through this heart. That propagation resulting in the collection of blood at atrias, and from atrias through maybe lungs, and then it comes to your ventricles, and from ventricles it goes to your body, and that is can be understood via this ECG signal or one cycle of ECG signal. So what it implies, this P wave, what it represents means the contraction of the atrias. When it gets contracted, your atrias, your blood will move from atrias to either ventricles or through to the some portion of your lungs. So that is your P wave representation. And whenever this electrical pulse is excited or it propagated at this junction, at the middle of the portion where the atrias and ventricles get divided, where you can observe another node called AV node, atrioventricular junction node. At this node, you will have some delay. So that delay represented by this PQ segment. Okay, this is called AV delay. And later, due to this ventricular contraction, as because in our heart, the ventricle is a high proportion. Maybe the volume of ventricle, especially the left one, is very high. So this contraction of QRS represents your left ventricular contraction. From left ventricular, your blood will pump throughout the body. Maybe sinus through aorta, it passes through your whole body. So that contraction is represented as QRS. And even later, due to some in action potential, you have something called repolarization and depolarization. So that delay causes this ST segment. This is due to the action potential. Some plateau region will be there because at every myocyte, the action potential is responsible for this. The accumulation of action potentials is only the any signal, whatever it is, ECG, EEG, whatever it is actually an accumulation of various action potentials. And finally, this ventricular repolarization, that is, your ventricles get relaxed for some time. That is represented by the T wave. So totally, this whole blood pumping mechanism is actually your ECG cycle. If there is any disruption in your particular heart or pumping mechanism, this wave gets changes. rhythm of that wave may change, the morphology of that wave may change. Hence, it is very important to understand the important nodes of each of signals, where you can see wherever you get some contraction, you got some peaks, P or T. So that peaks actually gives you a lot of information. Hence, it is important to find peaks. And even sometimes the R wave has very much significant between R wave and R wave using by, for example, here you have, see, this is R wave, R wave, R wave. So between each R wave, so how many number of R waves are presented in this particular segment is very important. Using that, we can calculate the heart rate. Heart rate can be computed using the R waves, number of R waves. Hence, detection of these R waves is important. In this signal, it is easy to detect R waves. But what about a signal which is of this shape? Just now we have seen something like this. Maybe signal. This is fine, this signal. Somewhere here, you will face some problems in identifying your peaks. Okay. And we have already seen one more kind of signal. So it's 1, 3, 4, 5, I think. See, detecting some kind of peaks here is very difficult. Hence, we need some algorithms to do this. So just I will let you know what algorithms are available. And just before that, we just use a simple command which is existed in the MATLAB. How far we can find that. Okay. So that is called peak. Let me use this peak detection algorithm. Okay. So what I'm doing here is I just take any ECG signal. Till this part, I'm just presenting my signal. Okay. And the one more change what I am doing here is I am doing some normalization, because generally my amplitude of ECG signal is the maximum amplitude of ECG signal is 1 millivolt. Hence, I am doing this normalization. Later, the thresholding is very important to the peaks of interest. So what are the important peaks we have to find is R and Q, R and S waves. These are called major components of your QRS complex. So QRS complex is this. So this is called your QRS complex, which actually tells you the ventricular contraction, which is important event of this heart pumping. So what I am doing is here the R wave can be detected by thresholding the peaks above 0.5 millivolts. So let me first show you this till this point. First let us run this program till plotting. Here you can see this is P, Q, R. This is R wave. This is above your zero point 0.5 millivolts. This is also above. Most of the times, your R wave is the highest peak among all other events. So what I am doing is I am doing a simple thresholding. However, this will not work for all kind of signals. What I am doing here is a simplest algorithm. So what we are doing is we are making a threshold. If any wave of any peak what we got, which is greater than 0.5 millivolts, I represent it as R wave. And S wave, if you see the R and S, they are separated by some time. How much time usually they have separated? You see here, this is your R and this is your S wave. They are separated by somehow some 200 milliseconds. So I just use that 200 samples. Okay. So R and S wave are separated by 200 samples. Hence, using that separation, I'll find another peak. So I just say these two are my R and S peaks. So that is the same operation. First, I find peaks for R wave using the command called find peaks. Very easy command, which returns you the magnitude of peaks the location of peaks, the width of peaks, the prominence of a peak. These are the outputs of find peaks. If you don't know anything about find peaks, I suggest you to just go here in command window. I'm sorry, and type here help and write here find peaks. You will get some information regarding the find peaks, or else you just go here search documentation, you will find peaks. And I am using these two commands and I just run. Let me show you what result you will get. As we don't have much time, I just hereafter I just run the program by telling you the essence. See, it identifies some R waves and S waves. The triangles represent R waves, squares represent S wave. However, sometimes you are missing some R waves and S waves. So you don't need this kind of algorithm. The algorithm should detect each and everything. So this can be done by using something called using this analysis called Pan-Tompkins algorithm. Using Pan-Tompkins algorithm, this is one of the famous algorithms. It follows some series of steps like filtering steps and squaring operation. So those steps I have explained here in this PPT. Maybe you can see here. Just this is the given ECG signal. I just do some band pass filtering operation to avoid both low frequency and high frequency components, and I just derivate this to enhance my peaks, and then I square, because if any component of less than 0, that is 0.01, 0.02 kind of thing, if you square, still it will diminish, and to improve this QRS complex. And finally we use some moving average filter for integration low pass filtering operation to find your R peaks itself. Later I just use some adaptive thresholding algorithm to find the peaks. So if I use that algorithm Pan-Tompkins, we can find the peaks. So what I am doing here is I'm using some Pan-Tompkins function here. Okay, the link also I have given in the PPT. Using this, we can find the QRS waves. It's taking some time. The steps will be available in this function. Today my system was a bit slow, but actually it is taking some time for plotting. But however, I got my result. Oh, okay, sorry. This is workspace of my previous problem. I'm sorry. Let it complete its process. I should have write here 1 so that I don't get any plots here. So for this CCC signal, I want to find my peaks. That's the idea. Okay. So why I got this signal analyzer, I will explain you it later. Now we got the results of our current problem. Yeah, I think I have put 0 here. Okay. So what will happen? See, it returns me 4 variables. One is QRS amplitude raw. That means wherever my R peaks available, the locations are here and their amplitude values given here. Okay. So these are the amplitude values of my R peaks, and the respective positions are here. Okay, now I got my R peaks. I can use these RR intervals for various other purposes. I can find some uh, heart rate analysis. I can do some heart rate analysis using these RR intervals. So that is another research area you can explore. Now, without any delay, let me show you some additional operations like filtering, which is one of the important concepts. Maybe let me show you one filtering process. Maybe 60 Hz noise. Let me take a power line noise. Maybe now this is a power line noise I'm using. So how do I know there is a power line noise here? I can write a spectrum estimation using my FFT mod FFT square operation. So this is my signal. Just by looking the signal, I don't know what frequencies lies in this particular signal. So what I should do is I should use this spectrum estimation. The spectrum estimation function was written by me. Maybe you can see here. So what I done is for a given signal, I find FFT and I have taken only the positive frequencies of one sided and I just did the square of this magnitude and log 10 operation to present it in a dBs. So that is one operation I can perform here to see what frequencies lies in my signal. So here at 60 Hz, I can find a peak. That is your power spectrum. So maybe some of you are not comfortable in writing such functions. The beauty of MATLAB here is already to do this kind of operations, some apps are available. So if you go to app, a signal analyzer app is there, which will return you what spectrum is there in the given signal. So simply I can use that signal analyzer here to do my operation. So this is Pan Tompkins function. What I'm doing here is I just write here signal analyzer of my ECG. So I got my signal. What I will do is I just write here my sampling rate. I will specify my sampling rate is 200 H. So in time scale, I got the signal. So here with respect to time. Now I just click on here spectrum. This is time domain. This is the frequency domain. At 60 H, you can find this plot. The same what we got using spectrum estimation. Okay. This I just got using my function, what I have written, or else you can simply use this signal analyzer to get what the peak which is not really important, which was light in this signal is 60 H. I just want to use this. What I commonly do to alleviate this process is I just use a notch filter where it will nullify this component. So we can do this by using some IR notch operation. So what I am doing here is I just use a notch filter, that is IR notch. The inputs to this IR notch is your W naught, which is actually your signal which one you want to nullify, as well as the bandwidth. You must specify it using a quality factor. Okay. Now if I use this, so this is function to design a filter. I have created a filter. It returns you the filter coefficients B and A. Since it is an IR filter, I have a numerator coefficients B and a denominator coefficients A. If you want to see the magnitude and phase responses, you can use two functions, either of these functions. One is frequisite or FB2. So let me use this FB2. There you will see the magnitude response of that filter. Exactly at 60 Hz, you will have some dip that implies at 60 Hz you will be nullifying your signal. Your pole is going to be 0. So see, it is in radians per second. That is the reason 0.6. At this frequency, you are not allowing that frequency. You are allowing up to 60 Hz and allow that. But exactly at 60, you are not allowing that frequency. So if I apply this filter on my signal, I have to use the command called filter. I have to pass my filter coefficients B comma A as well as my original signal ECG. If I pass this, is it an ECG? Let me clarify this. Okay, no issues. So now you see my filtered signal. You can find the difference. Okay. Okay. This is your original signal and this is your filtered signal. You can find the difference, right? This glitches or went away or gone away because you have removed that 6-stage noise. If you want to understand whether I have removed the 6-stage noise, again you have to use the signal analyzer where you have to now pass your ECG filter and see still that 60 noise is remained or not. See, this is where you can see a dip. You don't find that 60 noise here. So this is how you can filter your noise. Maybe if you want to remove your high frequency noise, or this is one higher notch filter. If you, this is also known as a comb filter. If you sorry, this is a notch filter. If you use a comb filter, even the periodics of this 60 can also be eliminated. And if you use a low pass filter, you can remove high frequency noises. However, I have done all those experiments, but because of less time, I am not going to show all those things. And let me show you some machine learning how to apply machine learning algorithms without writing a code explicitly to do the some pattern classification. So for that purpose, I am taking one database which reflects some epilepsy. So what I'm doing here is just it takes 10 minutes time. I'll show you. So all even frequencies filtering of EC signals you can do. So easy rhythm analysis can also be done using frequency. If you estimate your frequency as because based on how the bandwidth is, you can tell the signal is a delta rhythm or a theta rhythm or alpha or beta. Easy rhythm, easy signals were classified as rhythms, and each rhythm has its significance. For example, alpha is a very oftenly you will observe when your eyes were relaxed and in that region. If on the other hand, if you find the alpha rhythm when you are not in a relaxed position, then you can say that there is a problem with our body. So that likewise you can detect the pathologies. So by placing your electrodes on E scalp, you will find the EEG signals. So now we are doing some pattern classification for EEG signals that is called epilepsy detection. It is a central nervous system disorder in which brain activity becomes abnormal that causes a seizures or periods of unusual behavior. So if you got seizures of 1 or 2, maybe greater than 2 in a 24 hours of period, you can see there is a problem of epilepsy. So we are here considering an EEG database called Bond database, which consisting of 5 sets of ZO and FS. Z and O represents healthy patients. N and F represents interictal EEG or seizures, which implies just uh, the EEG is in between healthy situations and your seizures. And S represents complete seizure. So let me classify these signals. So for classification, what I'm going to do is, first of all, I have to find some features. First, let me find some basic statistics and classify. And later I will find another important parameters called Hazrat parameters, and I will find how much I am getting. Okay. Madam Desa, madam, shall I continue for 10 more minutes?
Hello, sir.
Madam,
Hi.
shall I continue for 5 or 10
Yes, sir.
minutes?
Please, sir.
Thank you.
Continue.
Thank you. So now let me do this easy classification part. So first Let me clear all variables and load my data. So I have loaded my data. As I told you, the data contains 5 sets of data. Each data is here contains 4097 samples, which is equal to the time period is about 23.6 seconds, because my sampling rate is 173.61. So 173.61 into 23.6, 23.61. Is it? I'm sorry. Is around here 4097 samples. So now what I am going to do is a binary classification. Let me do. I have collected the healthy patients, 100 healthy patients and 100 seizure patients data. Each contains 4097 samples. And let me plot you these two signals to see the difference between two signals in time domain. See, this is the data of my healthy patient, EEG data, and this is my EEG data of seizure patient, one patient data. Likewise, I have 100 patient data for healthy, 100 patient data for seizure. Now let me classify them. For classification, for I am using these parameters. So maybe this is ECG, EEG classifier, Hazrat. I'll do this Hazrat parameters later. Maybe basic statistics. Let me calculate this basic statistics first. So what I am doing is I am calculating the basic statistics. So what basic statistics I have considered here are, I have written a simple program for this function. I am taking a minimum of the signal, maximum of my signal, average of a signal, standard deviation of signal, median, and I have constructed a feature matrix for this. And now let me proceed with my classification. So later what I have done is I have constructed two feature matrix and I have assigned labels. For seizures, I have assigned a label called 1. For healthy, I have assigned a label called 2. And I have added those two data in one matrix called my final data matrix. My final data matrix size is, I have 200 patients. First 100 represents seizure, second 100 represents healthy. So the label, the sixth one represents seizure means 1, healthy means 2. That is my last column. I have to use this. So for this purpose, I can even write a code for classification, or I can use an app called Classification Learner. I have already opened this Classification Learner app. I just use a new session. So all the variables which were there in my workspace came here. I am interested in data matrix, and at predictor, my output is response. My response is my last column. Now I'm using some five-fold cross-validation. For validation purpose, you can use a cross-validation scheme or a holdout scheme. In a holdout scheme, what it will do is, it will split your data in randomly in percents, like 20% for testing, rest 80% for training, or you can change it. Cross-validation scheme, it segments your data into 5 equal parts for five-fold cross-validation. Each time, one part is for testing purpose and the other 4 parts for training purpose, and this process repeated for 5 times, and the average we will consider. So let me start a new session. Now my data will come here. So now it will give you some scatter plot here. So the scatter plot tells you the relations between your features. I calculated total 5 features: minimum, maximum, mean, standard deviation. And you see the first column represents first feature, second column represents second feature. So this is very implicit that these are clearly distinguishable if I use these two features. If I use column 1 and 3, how it would be, you can see. Still here is also very good to discriminate your data. So now I have a lot of algorithms available here. Just let me use the simplest algorithm called LDA, linear discriminant analysis. And let me do this train. Train will do both the cross validation scheme and give you the final output. Even